replicate currents n times. But now the interesting question is, can we make a better current source? Right? What do we mean by better current source? Well, one of the parameters that matter in a current source is how much the current changes with the output voltage. The less the better for it to be a better current source, right? Now, one of the how can we increase the output impedance of the state? What the state we are really using is a common emitter, right? And so the basic current here, if you look at it, looks like that. Now, this is a basic common emitter whose base voltage is kept at a constant voltage. You remember I said, well, I tell you somehow how we maintain these base voltages? This is one way to get the right base voltage, right? To bias it at the right voltage. That's exactly what I'm doing. This box is that simple version of that. Now, but the output impedance, looking into the collector of this thing, is RO of the transistor in this case. How can I increase it? Well, one thing that we saw works is emitter degeneration, right? If you put emitter degeneration here, if you have a resistor here, R, this output impedance would be what? Would be R out, would be, in general, the most general case, it would be RO on 1 plus GM or E1, and then RE over 1 plus GM RE over beta. And assuming that GM RE over beta is small, it's approximately RO times 1 plus GM RE. Okay? Now, but if you do this, just this, we know that the current is going to be very small. That would be the wide current source. Now, how can we keep exactly the same current? Let's say I wanted to replicate the IREF. I just needed to get exactly IREF here. And I wanted to get it at the higher impedance, output impedance. How do I do that?
Can you cascode it?
Well, no, just how would that help? Well, no, the problem here is that if this is IREF and if I put a resistor here, this current will become much smaller than IREF. Or smaller than IREF. Exactly, do the same thing on the other side. Exactly. Right? So if I do that, the new equations that I have is that this IR drop plus this VBE is equal to this IR drop plus this VBE. Right? In other words, IREF RE plus VT natural log of IREF over IS is equal to I out RE plus VT natural log of I out over IS. And you will see that if IS are equal and REs are equal, the only solution for this is IREF being equal to I out. Symmetrical, right? Assuming that the base current is small. Ignoring that. And if you can't ignore it, you can put the second transistor. So this is one way of getting a higher output impedance. Right? And I can increase my output impedance. What is the price I'm paying for something like this? Right. The headroom, the minimum voltage, minimum allowable voltage. So now if I look at it, the I out versus V out, it will start dropping at an earlier voltage. Where is that? What is that voltage? That's when this transistor starts getting into saturation, right? So that's when this voltage becomes, let's say, around DC sat, 0.1 volts, 0.2 volts, this voltage. But now, the output voltage, that voltage plus the voltage drop across this guy. So I've actually increased that minimum voltage by IREF. So this would be RE, IREF plus VC sat. So if the voltage drop across this guy is 0.5 volts, now instead of being able to drive this down to 0.2 or 0.1 volt, now I can only drive it down to 0.6 or 0.7 volts. Right? I'm losing on that. And depending on how much headroom or voltage headroom I have, this may be a problem. Well, if I'm running off of a plus minus 15 volt supply, it's not a big deal. It's not a whole lot. If I'm running off of a 1.0 volt supply, it's very important. So again, you see, whether or not this is significant or useful depends on the other parameters of the design space. Okay, so that's one way. Now, in general though, the higher this impedance, the better off I am, right? Because in principle, if I could make this very large, then I can actually get close to the limit of beta RO. Because if RE were infinite, in this situation, the output resistance would be what? Beta RO. But I don't want to make beta RE very large or infinite, because in that case, this voltage would be so large that this is practically useless. Right? Now, what can I use instead of that resistor that would give me a very high output impedance? So transistor, a cascode, right? So ideally, I want my output stage to look like that. Now, I need to maintain these voltages right. So I need to generate these voltages. So how do I do that? Well, I generated that one using a diode connected transistor, right? How do I generate this voltage? I want it to look kind of symmetrical, right?
You can use more diode connected.
Right, I can use another diode connected transistor. So if I do that, this is one diode connected transistor, this maintains these two VBs equal, and this is another diode connected transistor, right? And this is the output resistance. Now, let me ask you a trick question. What is R out? Well, unless you know the answer to this, there's no way. I mean, but what is the initial guess? I mean, my initial guess would have been beta RO. Right? Because the cascode now will give some cascode beta RO. But now there's an interesting thing in this stage. Because of this base current in RE, what happens is there's a second signal path through here. So a variation here, right? So let's say you change this node a little bit. You push it up a little bit. This node is the same node. They're shorted. This goes up a little bit. This goes up a little bit. What happens to this node's voltage? This VB drops a little bit. So this is basically up a little bit. This goes up a little bit. This is pushed up. It's basically, there's an inversion here. Basically, it corresponds to a change here. So there's some other mechanism. There's some second signal path through inside of this thing. And if you write down this, you actually draw the small signal model for this. These are simple. These are just 1 over R and 1 over Rn. I'm saying Rm, alpha Rm, alpha Rm. Diode connected transistors are easy. And draw the actual small signal model for this, and apply test voltage and measure the test current. You will see that because of the second signal path, this turns out to be beta RO over 2. Now, if I were to get the beta RO, exact beta RO, there's a way to do that, but nobody ever does that. Let me show you how. You want to get rid of this path, so you want to generate these two voltages as two independent voltages. Problem is that these are not exactly independent, right? They're coupled to each other. So what you can do, you can make an alternative branch here with diode connected transistors and another IRAF. Okay? And connect one of these to this branch and use this one to bias this branch. So you generate these two voltages independent, so they're not coupled to each other. These two voltages do not affect each other. If you do that, you get beta R. That's why I say it's a trick question, but there's no way to know actually what the answer is before you write the equation. But there is some tricky thing there. But nobody does this. Because beta R over 2 is large enough as well. So for practical purposes, that's good enough. Okay? So it's beta R over 2. And this is called a cascode current source. Now, let's look at the cascode current source. So we know its output resistance is high. So let's calculate its equivalent Thevenin voltage. You remember what the Thevenin voltage was, right? So the Thevenin voltage is the product of the RO and the current, which is basically the product of beta RO over 2 times the collector current. What is RO? VA over IC. So it's beta over 2, VA over IC times IC. So now you can see V out. How low can this voltage go before this stops being, at very high voltages, so this is relatively flat, right, because it has a very high output impedance. But at some point it stops being like that. So where's that point? How low can this voltage go? Well, I have to find out when one of the transistors goes into saturation. Right? These guys can't go into saturation. These guys can never saturate. So it's one of these two. The question is which one goes into saturation first? How do you determine that? Well, let's look at the DC levels. Nominal DC level. What is the DC level here, approximately, with respect to ground? 0.7, right? It's VBE on. What is the DC level at this node? Right, because this node is the same node as this, and then there's another 1. So what is the DC level here? Approximately. 0.7, right? It's another VBE drop down. So here is VBE on. This is 2 VBE on, and this voltage is around VBE on. So would this transistor saturate normally? No, because it's kind of more or less like this guy. These two have the same voltage. So it's this guy that saturates first, as I lower the voltage. As I lower the voltage, at some point this guy starts saturating. Where is that point? What is that minimum voltage? Exactly, 0.8, 0.9. It's VBE on plus VCE sat. So this minimum voltage here is VBE on plus VCE sat. Or for typical silicon transistors, from 0.7 volt plus 0.2 volts, so it's around 0.9 volts. You see that actually compared to the original bipolar version, that it could go down to 0.1 or 0.2 volts, it had only a minimum of VCE sat. Right? This guy has a much larger minimum, which is a bad thing. So that there's a trade-off involved there. So at this point, it starts going down. And then, okay? But if you need a high output impedance, that's the way to achieve it. Higher output impedance. Now, let me see. Now, how about the MOSFET version of this? Again, I can play the same trick in the MOSFET, right? In a basic character of the MOSFET, I had the RO transistor, but now I can make it into Cascode. So I still need this connection because I don't want these nodes to be floating, right? And this would be my output current, and this would be the reference branch, IREF, and so this is from VDD, and so on and so forth. So if let's say all of them have the same W over L. Now, what is the output resistance? What's the output resistance of this? Well, this one is not as tricky as the other one. What is R out? Yeah, that's the ballpark. So R out is approximately GM RO1 times RO2. Let's call this RO1 and RO2. Assuming that they are the same, this would be GM RO squared. But in principle, if they have different L's, they could be different. So in principle, it's product of 2 ROs. Approximately. And accurately, if you actually calculate this, I mean, we've done this calculation before, it is, so if you want to do it accurately, it is RO1, let's say let's call this RO1. This is 1, this is M1, M2. RO1 plus RO2 plus GM of this guy, GM1, plus GMB2, RO1, RO2. In this case, actually, you have to worry about the body effect in this guy. Because its source is not at the non-zero voltage. And in this case, in fact, this is connected in a common gate topology, right? The gate is at the constant voltage, the input is here, the output is there. And in the common gate topology, we saw that GM and GMB work in tandem, work together. Because both transistors were connected in a similar way. So, again, what you want, if you remember this is good enough. GM RO1, RO2. But if you want to do it accurately, this, or GM plus GMB, GMVR1. This is GM2. GM1 copper transistor. Okay? Now, so how about the output voltage, the minimum output voltage for this? Again, let's look at that. I out versus V out. What is it? Well, at very high voltages, this is a relatively constant, high output impedance source, so that's good. Now, the question is when it starts to lose its output impedance. So when is it going to stop being a good current source? Well, we need to calculate these DC voltages, right? What is this voltage here? DC-wise.
It's going to be the drain source voltage.
It's a VGS, right? Of this guy. But I can write a VGS as what? VGS is the VT. It has to at least have a VT for the transistor to be on, right? Plus the gate overdrive, delta VGS, which by definition, it's another way of saying this. Delta VGS by definition is VGS minus VT. Right? So now instead of writing it as just VGS, which I could, but I write it as VT plus delta VGS, the gate overdrive. But the same thing as saying it's a VGS. Okay? Now, if that's the case, what is the voltage here with respect to ground? 2 times that. Exactly. 2VT plus 2 delta VGS. And what is this voltage? The drop here is VGS, VT plus delta VGS. Right? So this would be VT plus delta VGS. So this transistor is in a situation where it's kind of like a dielectric transistor, right? Because both sides are at the same voltage. So this is not the way to try it. This is not the way to try it first. And at what voltage? What is the minimum voltage at which, minimum drain source voltage at which it goes into triode region?
VT plus
No, the drain source voltage, right? The condition for triode is that VGS minus VT is greater than VDS. But what is this VT greater than VGS? This is delta VGS, right? So at the edge of triode, VDS is equal to delta VGS. VDS. This voltage is delta VGS. So the minimum voltage here, the drop here would be just delta VGS. So the lowest voltage this can be is the sum delta VGS plus this. Right? So it's VT plus 2 delta VGS. At that point, it starts losing its output impedance. Does it make sense? Because this voltage at VT plus delta VGS, I need another delta VGS here to maintain this in the pinch-off region, and that's why I get 2 delta VGS. Yeah. Now, if I wanted to make this as small as possible, what can I do? Well, the delta VGS, what is delta VGS? It's VGS minus VT. I know what the relationship between ID and VGS minus VT is, right? ID is mu and Cox over 2W over L, VGS minus VT squared, which you can write as delta VGS over delta VGS squared, right? So delta VGS is square root of ID over mu and Cox W over L. So if I want to make my delta VGS as small as possible, what do I need to do? Well, usually I'm given a current level. I'm designing for a given current level, so I don't have control over that. Mu and Cox is a parameter of the process. I usually can't control that when I'm designing something. I'm left with W over L. So it says, well, make your W over L's large. Right? If I make them large, this delta VGS component of this thing can be made smaller. Albeit at the square root dependent, so I have to make it very large to make it very small. But nonetheless, I'm stuck with this VT. Right? Even if I get rid of this completely, there's a minimum voltage of VT, which I can't get rid of this arrangement. And that's a problem, right? I mean, because it's a VT of 0.6 or 0.7 volts. Or whatever it is. So, can you think of a way of getting rid of this? Why do I get that VT? Where is that VT transistors is having a lot more drain voltage than it could withstand. One of these transistors could be operated at a much lower drain voltage than it is now, without entering the triode. Which one is it?
The far left.
This bottom right.
So,
This one. This I can't do much about that. This guy, right? Because you see, its drain and source are at the same voltage, right? But this voltage could go much lower. It can actually be a VT lower than this, and still this transistor will remain in the pinch-off region, right? If this voltage, instead of that, were just delta VGS, I should be in a good shape. I'm still in a good shape, because if I could make this voltage somehow magic, delta VGS, then this voltage only needs another delta VGS, so this can go as low as 2 delta VGS, as opposed to a VT plus 2 delta VGS. So I can get it up as VT term. If I could somehow magically do this. How could I do that? Well, for this to be delta VGS, it means that this voltage has to be what? VT plus 2 delta VGS, exactly. So I need to drop a VT here somehow, magically. If I just have this magical battery with a VT, this would do the job, right? Agree? I don't have it, but if I did have that, I need to drop another VT here somehow magically. If I could do that, then this becomes 2 VT plus 2 delta VGS, and this becomes just delta VGS, and this can go as well as 2 delta VGS. So both of the transistors are just kept at the edge of where they enter the triode region when I get that. So I can go much lower. The question is, how can I do this? How can I do this? Well, what gives me a VT drop? Well, a MOSFET, right? The resistor, you say the resistor, but the resistor is, I'm trying to match the voltage across a resistor to a VT. That there are two completely different kind of thing. Maintained over all sorts of variations is almost impossible. So I have to get it out of another MOSFET, right? Between the drain and between the source and gate, the gate source voltage, in principle, could help me here. So what if I put a MOSFET, another NMOS, here, and let's say I just have a current source and use this. Would that solve my problem? I want this voltage to be what? So let's see what happens in that, if I just do that. And let's say this is the same W over L. If this works or not. This voltage was VT plus 2 VGS. What is this voltage? 2 VT plus 2 VT delta VGS. Now, what is this voltage drop across here? No, it's more than VT.
so it's VGS.
It's VT plus VG. That's right, it's VGS. It's VT plus delta VGS. Now, let's forget about this current source. I want this to be run at the same voltage, at the same current, right? So I can actually make this another branch of this guy. And make this W over L2. So all of them are running at these 3 branches have the same current. Fair? I could do that, right? So this branch and that branch and that branch all have I branch. I'm just kidding, I got rid of that current source, so that I made it simple. Now, this voltage drop, as you pointed out, is VT plus delta VGS. 30 years. This voltage is 2 VT plus 2 delta VGS. This is a VGS, as you pointed out, which is a VT plus delta VGS. If they're all the same W over L, they have the same current. So this would be a drop of that. So that voltage would be what? Just VT plus delta VGS. Right? What would that voltage be? The voltage of this row. 0. So that's not good. Right? I messed up. Because this guy then is going to need to try. That voltage is 0. So to get this up a delta VGS, this voltage needs to be a VT plus 2 delta VGS, right? And that means that this voltage has to be a 2 VT plus 3 delta VGS somehow. So I need an extra delta VGS here on this node. How do I get that?
Increase the width.
If I increase the width, what happens to the delta VGS? Width of what? If I increase the width, the delta VGS goes down. something about this W over L, right? How would I change this W over L so that the delta VGS is twice as large as the other delta VGS?
You can multiply 4 times or increasing.
Make it 4 times smaller. If I do that, its delta VGS would be twice as large. Therefore, I would get 2 VT plus 3 delta VGS here, and I get a VT plus delta VGS there, and I get a delta VGS there, which is exactly what I want, and then I get my headroom. So instead of that, I modify it to look like that. This would be 2 delta VGS. And then if I really want to if I want to minimize this, I can also my W over L of everything. Yes.
Doesn't that change the current on the right side?
On the which side? No.
Wasn't you changing the VGS of the transistors on the right side, top right?
Right. No, it won't. The first order, right? Because the current in this branch is controlled here. Right? Think about it. These are 3 current sources down there. This is the current source, this is the current source, right? So this current is fixed. Now, if I push this voltage up a little bit, this voltage will go up by the same amount, so its VGS remains the same. The current is determined by the VGS, right? So if I push this up, as long as this is high impedance, this will go up by the same amount. Do you buy this? Do you buy these 2 voltages? If you agree with that, then we don't have an argument, right? Because what happens is that if you agree with these 2 voltage levels, it means that the voltage across this is VT plus delta VGS. So its VGS has not changed. For a given current, it has the same VGS. So its drain voltage is not going to change. And it goes back to the fact that these currents are kept constant. First one. And this is just one example of the tricks you can play with MOSFETs that you can't do with bipolars. And we'll see a couple other examples throughout the course of these kind of tricks. By playing with W over Ls and looking at the levels, you can actually adjust it to the level you want. And what I've done here is that basically, what is this stage, this blue stage? With this input and that output. It's a follower, right? It's a source follower. You remember when we were talking about source follower, we said one of the uses of a source follower is a level shifter. So you can actually use it as a level shifter, a DC level shifter. And that's exactly what we've done here. We needed to make a minor modification to make sure that everything works out. Okay? Any questions on this? Okay. Now I don't think we have enough time to start talking about supply temperature independent biasing. We'll start that next time. So next time what we'll do, we'll talk about how to make these reference currents. But before we go, let's talk about something else. One more thing I want to talk about. Now, we've spent a lot of time on these MOSFET current sources, and I'll show you one example of PFET. But we can do everything that we did here in PFET as well. So if you want to use a Cascode current source, you can use it in PFET. And if you were to make a Cascode current source in PFET, it would look like this. And this would be the output. It makes sense, right? And you can play the same tricks here as you play there. Now, that's a current source you can make. Now, the other interesting thing about this Cascode current source, or the MOSFET version of that, is that, so if you look at it, well, or the NP, or you could do this with the PMP. So let me just show the PMP version. Now, interestingly, if you look at this, we saw that the output resistance of this guy was beta R over 2. Of course, it would be beta of the PMP R of the PMP over 2. But still, using the higher output resistance. Now, the interesting thing is that there's a variation of this kind of current source. So if you look at the NPN version of that, so this is the NPN version of that. Now, I could actually, instead of doing this, I could swap the transistor here on the lower branch that's dye connected. And now, if you do that, you have a current source that looks like this. And it's called the Wilson current source. Now, this one relies heavily on the feedback mechanism, right? Because if you look at it this way, let's say this node goes up, right? From here to there, what do you have? It's a follower, right? It's a common. So this one goes up, follows it. This node is the same node as that node, so this goes up. This node goes up, what happens to this node? What kind of stage do you have from here to there? It's a common emitter, right? So this is an inverting stage. It goes down. This goes down, what happens here? It's just diode, right? It goes down. So there's some negative feedback mechanism inside this stage. And if you go ahead, and I suggest you do it for your own, on your own time, your leisure, what you can do when you do that, and you can actually draw the equivalent model and calculate the output resistance. And for this one, it turns out that the output resistance is actually beta R. And again, I haven't proved that. Just told you what it is. You can draw this possible model for that, and you will see it. It's called the Wilson current source. So there's a variation of that, and the only difference is that you basically swap which transistor, the dye connected transistor from the left to right. And that's called the Wilson current source.
So that has a higher output impedance?
Right, the factor of two. Right.
But what's the drawback? Is you have
There's not a fundamental drawback. The thing you have to be careful about the feedback loop. Right. In terms of frequency response, that one is a little bit better than this one. We'll talk about it when we talk about frequency response. But there's no fundamental drawback. Any questions about all this stuff? You have a couple extra minutes if you want. Because I don't want to start the next topic right now. But the next time, what we'll do, we'll start looking at how we can make that reference independent of the temperature, supply, process variation. And we'll start again to go through the evolution of those things. We'll start from some simple things. We'll start with the simplest thing that we think might solve the problem. Then we'll see what the representations of that is. And then we'll take it through stages. And we eventually arrive at things that can make this completely independent of supply and temperature and all that. But now keep in mind, it's not necessarily a good thing to make this constant with temperature or supply. I'll tell you one reason. Just let me give you some very simple reason to think about. If I could make an ideal current source, right, which doesn't change with anything, with temperature. And let's say bias by state. Let's say I have a differential pair or a common emitter, doesn't matter. That's biased with that. And some resistors. Would that mean that the gain of this thing is constant? With temperature? What is the gain of this thing? What is the differential gain of this stage? GMR RC, right? So common emitter. I mean, for differential signal, it's just a common emitter. So it's GM RC. And what is GM? Right? I've made this one constant. But how about this one? What is that? KT over Q, right? IC over KT Q RC. This is constant. Well, this changes with temperature too, but let's say the resistor doesn't change either. Let's forget about that for a second. So let's say this is constant, this is constant. We make this one constant. This is a physical constant. This varies with temperature, right? So although I'm going to show you all sorts of things, it's not necessarily enough to make the current constant. In fact, for this, you want a non-constant. You want a current that's proportional to absolute temperature, or a p-tat. You want a current that actually increases linearly with temperature. And if you do that, then these guys cancel. So depending, I mean, we'll see that for MOSFETs it's different, and for different situations it's different. So we'll talk about how we generate all these different kinds of currents that have different kind of temperature dependence, and why we do them. But I want you to keep in mind that just the fact that this kind of current is absolutely constant doesn't mean it's a good thing. If you want to keep GMs constant in bipolars, you need p-paths, proportional to absolute temperature. Correct. Or a VT reference. But this VT. So next time we'll see how we can make a reference that depends on the VBE of the transistor. We'll see how we can do one that depends on the threshold voltage. We'll see how we can make one that's proportional to the VT of the transistor, the K2 over 2. We'll see how we can make one that depends on the band gap of the silicon material. And that's the one that's pretty much constant. Has the least amount of temperature dependence, and we'll see how that's generated. But if you want a constant voltage, that's a good thing. Alright, any questions? Okay. Well, I guess I'll see you then on Wednesday. We are going to have a tutorial next Monday, this coming Monday, at 10 a.m. that you and Megan will arrange, right? Organize.
Yeah.
For H-Spice. You're familiar with it? And only the H-Spice part of your homework is due on Wednesday. The rest of it is due on Monday. And if you haven't